Our study of the kinematic aspects of the special theory of relativity has now come to an end, and we are ready to start a new trip into relativistic dynamics. We will replace the classical formulations of physical quantities like force, momentum, and energy with new expressions in agreement with Einstein's postulates. Do we need relativistic definitions for classical dynamical quantities like force or energy? Yes, because the Lorentz transformation contains a much more complicated dependence on the relative speed. Let v be the relative speed between two references s and s prime, and let u prime be the speed of a particle in motion with respect to the reference frame s prime. If we make a comparison between the Galileo transformation for velocity and the corresponding Lorentz transformation, this much more complicated dependence is clear. Now, do not forget that v has a constant value in special relativity. As a result of this much more complicated dependence, it can be proven that acceleration has the same value in classical physics when we pass from one reference to another. Physicists state this, saying that A is invariant to Galileo transformations. On the contrary, acceleration has a complicated dependence on the relative velocity. Physicists state this, saying that A is not invariant to Lorentz transformations. As we said, acceleration is not invariant to Lorentz transformation. But what about force? Force has its own independent operational definition by means of a dynamometer. We set up the scale of force in a reference frame, but when used in a different frame, will it produce values that change in the same way as acceleration does? Here we have the famous Newton's second law of dynamics. As we said, Lorentz transformation contains a complicated dependence on the relative speed. Therefore, acceleration changes in a complicated way from one reference frame to another. What about transformations for force? Well, there is no reason why force should transform in the same way as acceleration and maintain the classical form of Newton's second law. Therefore, Newton's second law assumes a different form in relativity. Instead of studying how F equals ma changes, we will focus on the law of conservation of momentum. Momentum in italiano si traduce con quantità di moto, not to be confused with moment or torque, che è invece il momento di una forza. To illustrate, consider a force, a constant force for simplicity, acting during an interval delta t on a point particle whose mass is m. F equals ma, and if we expand A, we get m times delta v over delta t. And if we multiply both sides of this equation by delta t, we are left with f delta t equals m delta v. Now imagine the case when no force is acting on this point particle. We cancel off the first-hand side of this equation, and we are left with 0 equals m times delta v. If we expand delta v, we get m times the final value for velocity minus m times the initial value of the velocity. We can now define a new physical quantity we call momentum. P equals m times v, and this equation can be written as P2 minus P1, which is the value of the momentum after the action of the force F minus the value of the momentum before the action of the force F. Therefore, when no force is acting, P2 equals P1. You can state this by saying that momentum is conserved. Why do we prefer to express physics in terms of conservation laws? One might wonder the reason why we introduced a new physical quantity like momentum, and the answer is that physics is better when expressed in terms of conservation laws, because a conservation law is always a more fundamental statement, since it requires the definition of just one physical quantity. To illustrate this aspect, the law of conservation of momentum is a theorem in classical mechanics, since it can be derived from Newton's second law, as we did. But outside the domain of classical mechanics, it is a fundamental principle, and it is demonstrated only by means of observations. Now, an important aspect of momentum is that it depends on the reference frame. To illustrate this point, simply consider that a passenger holding a ball on a train sees it having no momentum since it is standing still in his hands, differently from an observer that looks at the same ball from the railway station. According to this second observer, the ball has the speed of the train and therefore it has a non-zero momentum. Now, since time also depends on the reference frame, as we know, we expect that the classical definition for momentum P equals mv has to be reformulated in the special relativity. A simple example where we can apply the law of conservation of momentum is an elastic collision, namely a collision where energy is conserved between two identical spheres in one dimension. Sphere A is traveling at a speed va in direction of sphere B, which is traveling at speed vb in direction of sphere A. Since the two spheres are identical, ma equals mb, and if we write the momentum of this system before the collision, we have the vector relation p1 equals ma times va plus mb times vb. In the instant of the collision, body A exerts a force F on body B, and according to Newton's third law, body B exerts a force minus F on body A in the opposite direction but with the same magnitude. Therefore, the overall force is zero, and since a null force is acting, momentum is conserved in this system, and we can write P2 equals P1. Now, there is a very simple way to satisfy this requirement, and it is to swap over the velocities. If B emerges from the collision at speed va and A emerges from the collision at speed vb, since the masses are equal, the momentum of the system after the collision is equal to the momentum of the system before the collision. It is easy to see this if we replace ma and mb in these two equations with their common value m. Therefore, an important conclusion to bear in mind is that an elastic collision between two identical spheres exchanges their velocities. Therefore, the only case in which velocities are simply reversed is when they have the same magnitude. Another example, a two-dimensional elastic collision between two identical spheres having opposite speeds. Let ma and mb be their common mass and vb equals minus va their velocities. When they are not moving too fast, classical mechanics holds. Therefore, momentum is conserved. Before the collision we have p1 equals 0 according to these relations. Now, let us consider the instant of the collision. We have two very strong impulsive forces, opposite in direction but having equal magnitudes, and directed along the line that joins the centers of these tiny spheres. We choose a y-axis parallel to the direction of the impulsive force and an x-axis perpendicular to this direction. This is a vectorial relation. Therefore, once we have chosen our reference frame, momentum has to be 0 along both our axes. Let's now decompose the velocities and apply the vectorial law of the conservation of momentum along both axes. Momentum has to be 0 after the collision too. Here we have the x component of b and the y component of b's velocities, and the x components of a and the y component of the velocity of a. And these are the particles emerging after the collision. Along the x direction, no force is acting since we assumed no friction at all for an elastic collision, and no change of direction is observed along x. Therefore, to satisfy the conservation of momentum, the x components just have to remain unchanged. So, VA was in the direction of the x-axis and it remains along this positive direction. VBX was contrary to the positive direction of the x-axis and it remains contrary to the positive direction of x after the collision. Along the y direction, things are different. And no force is acting, but we see the y components of both velocities to experience a directional change. The y component of the b velocity is pointing in the positive direction of the y-axis, and it is pointing contrary to the positive direction of the y-axis. The y component of the particle A is pointing contrary to the positive direction of the y-axis, and it is pointing in the direction of the y-axis after the collision. Therefore, the situation is analogous to the one we studied for a one-dimensional collision. the conservation of momentum requires the particles to exchange their velocity components along the y direction. In this case, since the speeds were identical before the collision, the exchange means simply that the y components are reversed. We are now ready to answer the question whether momentum is conserved at relativistic velocities. Here we have the same collision. To establish whether the momentum in the classical form P equals mv is conserved, we will now assume that A and B have relativistic velocities along the x-axis. Let us view this collision from another reference frame S', in which the particle B has an x component of velocity which is 0. B has only a non-zero y component of the velocity, whilst A has both components which are non-zero. This is the path followed by A and this is the path followed by B, and the collision takes place over here. Here we have the collision in our reference frame S'. Now, since y is the direction of the impulsive forces during the collision, as we have seen, the y components of velocities are reversed on collision, whilst the x components remain unchanged. Therefore, an experimenter in S' sees particle B to be moving parallel to the y direction, having a non-relativistic velocity which is reversed on collision. As for particle A, it sees it having a relativistic x component of velocity. We will denote it simply by v, unchanged by the collision, and having a non-relativistic y component of velocity reversed on collision. But the most important thing is that because of the presence of the relativistic velocity component along the x-axis possessed by A but not by B, an experimenter in S' sees A to be experiencing a time dilation. Now, since the y components of velocities are non-relativistic, there is no length contraction along the y direction. Therefore, also in S', they collide halfway in the y direction, traveling both a path of the same length along the y-axis. But A travels the same distance along the y-axis in a time longer by a factor of gamma with respect to B due to its time dilation. Therefore, since to an observer in S', A is seen to be traveling the same distance in a longer time, we must conclude that in S', A is traveling along y at a speed slower by a factor of gamma with respect to B, namely Vya equals minus Vyb over gamma. This speed is slower than this other speed, and this means that the classical momentum is not conserved in S'. And the reason why the classical momentum is not conserved is because the collision reverses along the y-axis the motion of two particles with the same mass but different y components of velocity. As we know in classical mechanics, the only case when the two velocities are reversed is when they are equal. Therefore, In classical mechanics, this effect is simply not possible. Let us recap what we know. An elastic collision between two identical spheres exchanges their velocities. A emerges from the collision at a speed vb and B emerges at a speed va. The only case in which velocities are simply reversed, namely A emerges at a speed minus va and B at a speed minus vb, is when the initial values va and vb are equal. But as we have seen in our collision at relativistic speeds, along the y direction we have a reversing of velocities even if their values are not equal. This is simply a different way to say that the classical momentum is not conserved along the y direction. But what should we change in the classical momentum definition P equals mv if we want the momentum along the y direction to be conserved? The idea is simple. It must be that relativistic momentum of A in S' is increased by the same factor gamma, by which the transverse velocity of A, the y component of the velocity, has decreased. Therefore, the classical momentum definition does not hold in relativistic mechanics, and we must replace it with a new definition, P equals gamma times mv, which we call the relativistic momentum. Let's now see whether the relativistic momentum along the y direction is conserved in our collision. Before the collision we have Py equals m times gamma Vay, since A is traveling at a relativistic speed, plus m times gamma equals 1 here because B is not traveling at relativistic speed by Vby. If we remember that Vay is slower by a factor of gamma with respect to Vby, as we have seen due to the time dilation effect, and we replace here this value, we get two gamma factor which cancel off, and the final result is 0. Therefore we have Py equals 0 before the collision. After the collision, P'y equals m gamma V'ay plus m times 1, which is the gamma factor for B, times V'by. If we replace this V'ay with minus Vay, since velocities are reversed along the y direction, and we know that the Vay velocity is equal to minus Vby over gamma, we get here two gamma factors that cancel off and a final result of 0. Therefore, momentum along the y direction is 0 both before and after the collision, and the classical momentum is not conserved, but the relativistic momentum is conserved in the collision. What is the connection between classical momentum and relativistic momentum? If we expand the gamma factor, we get the square root of 1 minus v squared over c squared at the denominator, and it is easy to see that as v becomes negligible with respect to c, namely as v squared over c squared approaches to 0, and therefore gamma approaches to 1, since we are left with just 1 here at the denominator, the relativistic expression for P reduces to the classical form, since gamma here is equal to 1. Now, if we plot this expression for the magnitude of P in a P v plane, we get a curve with an asymptote as v equals c. On the other hand, the classical expression for momentum is a line that goes through the origin. Therefore, these two behaviors are very similar at non-relativistic speeds, but as v over c approaches to 1, namely as v approaches to c, the relativistic momentum approaches infinity. With respect to the formula P equals gamma mv, many physicists prefer to think of point particles' mass as speed-dependent and associate gamma with mass in order to have P equals mr times v, where mr is called the relativistic mass. The relativistic mass is a physical quantity that grows with particle speed and approaches infinity as v approaches c. If we plot the relativistic mass versus the speed v, we get a function with a vertical asymptote at v equals c, and whose value is equal to m when the speed is 0. On the other hand, many other physicists choose to maintain the use of Newtonian mass as an invariant property of matter, and this because they say that there is no way to have a direct measure of the mass of a moving particle, but all that we can measure is the change of particles' momentum with speed. Now, both these views are possible, and even Einstein himself changed his mind about these two interpretations during his lifetime. We are now ready to look for a relativistic expression for kinetic energy for a point particle. As we know, at non-relativistic speeds the laws of classical mechanics hold, and the expression for kinetic energy of a point particle is kinetic energy equals to 1/2 mv squared. At these low speeds, v over c is much smaller than 1, and we can make a useful approximation for gamma. Gamma equals 1 over the square root of 1 minus v squared over c squared is almost equal to 1 plus 1/2 v squared over c squared. This approximation holds only for values of v squared over c squared much less than 1. Now let's multiply both sides of this equation by mc squared so that we get a gamma mc squared at the first hand side. Here 1 becomes mc squared, and 1/2 v squared over c squared by mc squared becomes 1/2 mv squared. As we know, we've got the classical kinetic energy expressions at the second hand side. Therefore, this is equal to mc squared plus the kinetic energy. And if we solve with respect to the kinetic energy, we have k equals to gamma mc squared minus mc squared, or gamma minus 1 in brackets times mc squared. A more rigorous analysis, which we are not doing here, proves that this expression is valid not only in the limit v much smaller than c, but that it holds for all speeds. Therefore, an expression for kinetic energy of a point particle in relativistic mechanics is gamma minus 1 times mc squared. So far for the kinetic energy of a point particle, but what about the total energy of a free point particle? In classical mechanics, the total energy of a free particle corresponds to its kinetic energy. However, in relativity, things go differently, since we have found an expression for kinetic energy which has the form of a difference of the same quantity gamma mc squared, namely, this is the quantity gamma mc squared evaluated at speed v, and this is the same quantity evaluated at speed v equals 0 and gamma equals 1. This suggested Einstein an idea. The kinetic energy of a free point particle can be obtained by subtracting from the overall energy, whose form is gamma mc squared at speed v, a quantity that Einstein called the rest energy E0 equals mc squared, which is independent of velocity. Therefore, we can write k equals E minus E0, and solving with respect to E, we have that the total energy of a free particle is equal to its kinetic energy plus its rest energy. And if we replace k and E0 with their expression, we cancel off this mc squared factor over here, and here we have the total relativistic energy for a free particle, E equals gamma mc squared. And if we want to use the relativistic mass, we have the more famous formulation E equals mc squared, where mr is not the Newtonian mass but the relativistic mass of the point particle. Why can't a massive particle reach the speed of light? In the expression for the energy of a free point particle, consider first the case v equals 0 and gamma equals 1. What we have is an isolated particle has energy even if it is not moving, namely even if its kinetic energy is 0. Now, let's expand gamma. It is easy to see that when v approaches the speed of light, the denominator approaches 0, since we get 1 minus 1 over here. Now, since the denominator gets smaller and smaller, the whole fraction gets larger and larger. This means that as v approaches c, the energy of the point particle approaches infinity. Therefore, you need an infinite amount of work to reach C. But no real force can do an infinite amount of work. And this means that no massive particle can reach the speed of light. If we plot the quantity v squared over c squared as a function of the kinetic energy, we can see this behavior in the graph. We get a curve with an asymptote at v squared over c squared equals 1, and real forces can only provide finite amounts of energy here to increase kinetic energy along the x-axis, but no matter how large is the amount of work they do, you never overcome this limit, which is an horizontal asymptote to the kinetic energy. Therefore, you never overcome the speed of light. In classical mechanics, the same plot is a straight line through the origin, and you can reach whatever speed value you want. Moreover, due to this asymptotic behavior, it can be proven that progressively larger increments of energy are necessary if you want to accelerate a particle as its velocity approaches to c, namely, the amount of work you need to increase speed here is less than the amount of work you need to increase the particle speed in this region very close to the limit. We have found that the total energy of a free particle is equal to its kinetic energy plus its rest energy, and the rest energy is in relation to the particle's mass. But in what sense can we say that energy and mass are equivalent? Are energy and mass the same thing? Are they simply proportional to each other? These questions are still being discussed, but from an experimental point of view, what we observe is that massive particles can be transformed into electromagnetic radiation, which is massless. To illustrate this, consider that when an electron collides with its antiparticle, a positron, they annihilate and they are transformed into electromagnetic radiation. Therefore, we are able to turn mass into energy and also energy into mass. So we can measure energy in mass units and mass in energy units because we have now just one concept, namely the mass energy. This is pretty similar to what James Joule did in the 19th century when he measured that 1 calorie was equal to 4.186 joules. Let us calculate the rest energy equivalent of 1 kilogram of mass. We have E0 equals mc squared, which is equal to 1 kilogram times the speed of light 3 times 10 to the 8 meters per second squared, and the result is 9 times 10 to the 16 joules. In particle physics, masses and energy are small. Therefore, physicists prefer to use a unit of measure much smaller than joules, the megaelectronvolt. 1 megaelectronvolt is equal to 1.602 times 10 to the minus 13 joules, so it is a tiny unit of measure for energy with respect to everyday phenomena, but it is suitable for the rest energy of electrons and protons. For the rest energy of an electron we have m electron times c squared, therefore we multiply 9.109 times 10 to the minus 13 kilogram times the light speed squared over the number of joules per mega electron volt, and the result is 0.511 mega electron volts. And for the rest energy of a proton, whose mass is almost 1800 times the mass of an electron, note the exponent that changes from 10 to the minus 13 to 10 to the minus 27, the rest energy is 938 mega electron volts. Also, we prefer to give mass in units of mega electron volts per c squared, and this simply in order to avoid the division by c squared. Therefore, the electron mass is 0.511 mega electron volts per c squared, and the proton's mass is 938 mega electron volts per c squared. Language of learning. You say the magnitude of a vector, l'intensità di un vettore. The magnitude of the velocity vector is 30 meters per second. You decompose a vector into components. Let's decompose the velocity into its x and y components. You swap over or you exchange something with something else. The y components of velocities are swapped over. You say a segment that joins 2 points. The segment that joins A and B. You say the left or the right-hand side of an equation, or the first or second-hand side of the equation. The left-hand side of the equation can be written as language of learning. You say that 2 quantities are proportional to each other. Energy and mass are proportional to each other. You make a division by... You can't make a division by 0. A quantity can approach a number, or it can approach to a number, or it can approach infinity. As the speed approaches c, the kinetic energy approaches infinity. You say a line that passes through the origin or through 1, 2. The graph is a line through the origin. The equation represents a line passing through 3, 4. Language of learning. You say to exert a force, and with opposite meaning, to experience a force. If object A exerts a force F on object B, then object B exerts a force minus F on object A, or object A experiences a force minus F. You say collision, to collide, to emerge from the collision. Object A collides with object B, and B emerges from the collision, moving at speed v. You travel along or contrary to the positive direction of the x-axis. You can also say to travel in the positive direction of the x-axis. The velocity is contrary to the positive direction of the x-axis. And you say the graph has a vertical asymptote at x equals 3, or a horizontal asymptote at y equals 2. Language of learning. You say, on the contrary, to introduce a statement that says the opposite of the last one. Acceleration is invariant to Galileo transformation. On the contrary, it is not invariant to Lorentz transformation. But you say to the contrary when you prove the opposite. The speed of light in vacuum has always the same value, and nobody can show evidence to the contrary. You satisfy a law, apply a law. To satisfy the conservation of momentum, the x-component of speed is unchanged on collision. We can apply the law of conservation of momentum. And you say, after a law. After Newton's second law, force and acceleration are proportional to each other, che non si traduce in italiano con dopo la seconda legge di Newton, bensì in conseguenza della seconda legge di Newton, la forza e l'accelerazione sono proporzionali.